To start for Chapter 11, we're going to look at a question where we're going to go through some of the intermolecular forces that affect molecules and see how we need to evaluate that. So I'm going to start with question A. For A, we have the molecule C3H8. So if you can just look at that and tell the intermolecular forces, that's fine. For each of these, I'm going to make a Lewis structure, though, because that helps me out. But if this isn't required for the exam. If you know how to just look at that and know it's only dispersion forces, you are A-okay. But just in case, I'm going to do this myself. So when I do this, I note that there are 3 carbons and 8 hydrogens. That'll fill up all of these. And so what you'll notice is we have carbon-carbon bonds. That's an atom bonded to itself. There's no electronegativity difference. That's nonpolar. And we said we were going to treat all carbon-hydrogen bonds as nonpolar bonds. Like that was just one you needed to know. That was the only one I asked you really to know outside of just atoms bonded to themselves. So CH bonds are nonpolar. Everything here is nonpolar. That means we have a nonpolar molecule. If it's nonpolar, that means we are only going to deal with dispersion forces. Remember, these can also be called London dispersion forces, or they can be called van der Waals forces. But I'm going to try to use the term dispersion forces as often as I can consistently do so. So for A, just dispersion. So this is A. Now, let's look at B. So for B, we have a nitrogen atom. It's our center, and it's bonded to 3 hydrogen atoms. Remember that we're not going to be able to have hydrogen as the center, so we know nitrogen has to be the middle. Note that I'm not worried about the orientation of these 3 hydrogens. I am drawing it because this is what I know it would normally look like, because it's going to form a trigonal pyramidal molecule. But if you don't, that's okay. I'm not going to be like, oh no, you drew your hydrogen in the wrong spot because you drew it this way. This is A-okay as long as you get the Lewis structure right with the dots. So when I do this, NH3 has 8 total electrons, and we've only used 6 in our lines, so we need another 2 here to give us a total of 8. If you drew it this way, you'd also have your 2 dots here. What's important to note about this molecule is it contains NH bonds, and that they're not going to be symmetric, so there's going to be some canceling out, so there's not going to be a canceling out effect for any dipole you would have. And because it's specifically nitrogen bonded to a hydrogen, we can also have hydrogen bonding. Remember, that comes from fluorines, oxygens, and nitrogens bound to hydrogens. That's when we get the hydrogen bonding effect. So for B, we have dispersion, because all molecules are going to have dispersion forces, and that's our weakest. Then we'll have dipole-dipole, because we have a polarity difference. And then we are also going to have hydrogen bonding, which you can also just write H bonding, or you can write hydrogen bonding. It's okay either way. So for B, we have dispersion, dipole-dipole, and hydrogen bonding. Make clear. So now let's look at C. So for C, this is one where it's going to show up why you need to know how to do your Lewis structures. So we're going to start with carbon bonded to 2 oxygens. We have a total of 6, 12, 16 electrons. We've drawn 4, so you have 12. Note, if you know how to do this, it's fine not to draw out this step right here. But I will point out that while I'm doing CO2 as practice, it's reasonably likely you will have something other than carbon dioxide to have to do on the test. So make sure you can do this with other cases. So we start filling up our electrons until we fill up the outsides, we run out. So we put 12 electrons, 6 on each oxygen, and that's all we have available. There aren't any more for the carbon, but the carbon needs a full octet. If you remember from your Lewis structure rules, that means we're going to need to borrow some, and specifically carbon is going to need 2 sets of shared because it needs a total of 8 electrons, but only has 4. So we end up with carbon dioxide like this, and so even though the CO bond can be polar, these are exactly opposite each other as it's a linear shape, so they would be able to balance each other out. So there would be no dipole-dipole forces. This is going to be dispersion only. We'll then finish with HF. So with HF, we end up with H bonded to fluorine, 3 sets of electrons. Fluorine is way more electronegative than hydrogen. That means we have dispersion. We have dipole-dipole. And we also have hydrogen bonding again because this is one of our 3 atoms that can hydrogen bond when bonded to a hydrogen. So fluorine, oxygen, nitrogen. That's an example of intermolecular forces stuff. Now, while this is the only one I practiced, you should also be able to rank the strength of the intermolecular forces, and you should be able to do problems where you have sets of molecules and you have to sort them. For example, if you had something like CH4, C2H6, C3H8, you should be able to tell me which has the strongest dispersion forces and the weakest dispersion forces. The same with dipole-dipole as well, and with our hydrogen bonding stuff. So you should be able to do that for each of these, and there are problems in the recommended text that work through that, although I don't have an example here because this is a limited set of problems. So next, we're going to go and we're going to look at a conversion factor using enthalpy of vaporization. So if the enthalpy of vaporization is 38.6 kilojoules per mole for ethanol, how much energy is needed to vaporize 18.6 grams of ethanol at the boiling point? So since we're at the boiling point, there's no need to heat or cool this down. We know it's ready to be vaporized. If it wasn't at the boiling point, you might need to do a heating curve type problem and do some Q equals MC delta T stuff. But we don't have to worry about this. We're at the boiling point. We're ready to vaporize this stuff. So we know we have 18.6 grams. We know that from the molar mass is 46.08 grams of ethanol makes 1 mole of ethanol. Then from there, we can use either, if you prefer it, you can use this equation, Q equals N delta H vaporization, plug it into there. Since we're just doing this one step, I like using this as a conversion factor itself and putting that 1 mole equals 38.6 kilojoules. Note that both will give you the answer, but I like doing it this way when it's just a one-step problem. It makes it easier to get through. And when I do the math for that, my grams are going to cancel, and my moles are going to cancel, and I'm going to end up with 15.6 kilojoules. So you notice that this is a problem that you have to identify that because it's the boiling point, you're able to just do the phase change right away without a temperature change. So hopefully this is a problem you become where you can recognize it. You should also know that it doesn't have to be vaporization, right? I could have instead asked for you to do condensation, like it was at a gas and it was ready to turn back into a liquid. And then you would just have to take the negative of your vaporization because you would be removing the same amount of energy that you had to add when you were vaporizing. You can also do it for things like sublimation and deposition or fusion as well, when we're either melting or freezing. So make sure you can do all of those different ones and you have a feel for them. So now let's do something where we're going to look at instead a Clausius-Clapeyron type question. So one way I know this is we start talking about vapor pressures, and I'm given a few numbers. I'm given the heat of vaporization. That's a hint that it might be Clausius-Clapeyron. I'm also giving a normal boiling point. And remember, that means that I'm actually getting two pieces of information. I'm getting a pressure and a temperature when I'm told that it's normal, because normal means 1 atmosphere or 760 torr. And then finally, I'm given another temperature and asked for a vapor pressure. This looks like a Clausius-Clapeyron 2-point equation to me. I wouldn't want to use the 1 point because I would then I would probably need a graph for that, or at least an equation for a line, or I would need a lot of data points if I were doing it for a lab where I could come up with that. You can't do a 1-point version from just a small set of data. You need a large number of data points so you can come up with a line, an equation that represents that. So that's what we did in lab. So I'm not going to worry about that one as much. Since you're doing that in the lab class, we're going to focus on the 2-point conversion here. So for this one, we have the equation ln P2 over P1 equals negative delta H vaporization over R. And I'll point out, yes, there's a reason that I type everything because my handwriting is not all that perfect, but it'll work. And times 1 over T2 minus 1 over T1. This is our Clausius-Clapeyron. So what I like to do first, if you're not sure, is identify what it is you know. So we know, I'm going to write this over to the right, we know P1, I'm going to set P1 to 1 atmosphere. Okay, we'll make that there. You don't have to set you could set P2 to that. You just have to be consistent. That means P2 is question mark. I don't know the vapor pressure. T1, it's very important this matches up with the choice for P1. So P1 is the normal boiling point, is 1 atmosphere. So this T1 is 78.4 degrees Celsius. And then if I add 273 to it, I'm going to get that it's 351.4 Kelvin. We then have T2, which is the one we're searching for, the pressure at, and T2 is equal to 22.0 degrees Celsius, and that's equal to 293 Kelvin. So now we can do this a few ways. Oh, right, delta H vaporization. Delta H vaporization is equal to 28.56 kilojoules per mole. And I'm going to go ahead and convert that to joules, since I'm going to need that so it matches with my units for R. So I'm going to go ahead and say that it's 28,560 joules per mole. So one option is to plug all these numbers in and then just keep solving things until you get P2 by itself. I am going to rearrange everything first, but you don't have to do that. So what I'm going to do first is I'm going to raise everything to the E power. So E here, these cancel. I'm left with P2 over P1 equals E to the negative delta H vaporization R 1 over T2 minus 1 over T1. Then I'm going to multiply both sides. And remember, P1, I'm going to multiply both sides by P1. If you notice that P1 is 1 atmosphere and won't change anything, you wouldn't have to do this, but you can. So P1 times E negative delta H vaporization over R times 1 over T2 minus 1 over T1. So then I'm going to plug all my numbers in, and I'm going to get P2 equals 1 atmosphere. So that's going to get me in the right units. It'll put me in atmospheres, which is good because pressure, the exponential is not going to have a unit. So we want this to be an atmosphere since that's what pressure would be in, or torr, or just some other unit like that, some pressure unit. Then when we plug all this in here, we're going to get negative. Don't forget this negative. A lot of students have been doing that, I noticed, because it's just hard to remember because you don't think about it all that much. Negative 28,560 joules per mole over 8.314 joules per mole Kelvin. Remember, that's just a constant you're going to have on your equation sheet. We then have 1 over T2, make sure we don't flip these, 293 Kelvin, minus 1 over 351.4 Kelvin. So from here, close my parentheses again, we can plug all of this in, and when you do, I have to be away from the corner because that does weird things. There are buttons down here. So P2, when you put all your numbers in, is going to give you 0.142 atmospheres as our vapor pressure if we are at 22 degrees Celsius. So that's what we would do if we want to use the Clausius-Clapeyron 2-point. You can also solve it if it gives you a vapor pressure for another place and wants to know a temperature related with that, so you can do it both ways. But this is how I would do it if I was trying to solve for P2 for a pressure. The other way, you just have to rearrange and get temperature by itself. So now, let's look at a heating curve question, because we've been doing some stuff with Clausius, but I know these there's a lot of information in some of these. So we have how much energy does it take to cool 10 grams of gaseous ammonia from 25 to negative 55 degrees Celsius, and then a giant dump of information. So what I want to figure out first when I'm doing a heating or cooling problem is, are there any phase changes? How do I need to split up my problem? So what you look at is your melting and boiling points to see if they occur during your temperature change. So we're going from 25 to negative 55, and you'll notice the boiling point is negative 33.34, so that occurs in the middle of that. Well, the melting point is negative 77.73, so that isn't part of this problem. We don't need to melt anything. We're not going to have any solids, so we don't have to worry about solid stuff. Makes it easier. And that also means we don't actually need this delta H fusion. You're not going to use it. You're not turning it into a solid. So if I were to think of this just in terms of what I'm going to do, I'm going to go from 25.0 degrees Celsius. I'm going to shift that to negative 33.34. I'm then going to phase change. And specifically, we're going to condense. And then we've got to finish cooling down. So we're going to go negative 55.0 degrees Celsius. I'll also note that we're cooling down. So since it says how much energy does it take, the answer is going to end up negative because I'm removing heat from the system, because that's how I'm going to cool something down. So you don't have to write down this string right here if you don't want to. You can just do each step. But this can help sometimes if you're not sure how to organize it. So first figure out what are you going to have to take into account. This shows we're going to have a Q here for heat, for cooling. Here we're going to have to use our delta H vaporization, which we're going to have to change into delta H condensation, since we're condensing instead of vaporizing. And then we've got to do another Q equals MC delta T here. Remember, all three of these are Q's, but you're just using slightly different equations. So we're going to start with the first step. There's my pen. So Q equals MC delta T, and I'm going to do this for the first section. So Q is going to have a mass of 10.0 grams. And at first, remember, you want to think about what phase you're in. For 25 to negative 33, you're currently in the gas phase, so you need the specific heat of the gas. And so that is going to be 2.06 joules per gram Kelvin. Then you're going to look at the temperature change, and I've gone ahead and changed it into Kelvin on my side. If you understand why you can keep this in Celsius for this specific calculation, that's okay, but you should understand why, and if not, you can change it, and that makes sure that you don't run into any problems. So we have 239.66 Kelvin is our final temperature, minus our initial is 298 Kelvin. When we put all of this in our calculator, we're going to get negative 1,202 joules. And I'm going to go ahead and convert this to kilojoules since everything needs to be in the same unit at the end. And I'm going to get negative 1.20 kilojoules is what I'm going to use. This is step 1. Now our step 2 is our phase change. For this, we first need to recognize that delta H condensation is going to be equal to negative 1.37 kilojoules per mole. This is because condensation is the opposite of vaporization, so we have to change the sign for that. Rather than being positive, it'll be negative. We can then plug it into our equation, and this time I'm going to use the equation. You can also use this as a conversion factor, like we did on that second question I was doing. Both work fine. And for this one, we also need moles. So I expect that you can do that calculation on your own, but if you take 10 grams of this should say gaseous methane on the top. I am sorry. All these numbers are for methane. I had written an ammonia problem and had problems. These numbers are for methane. Yes, we want to keep this. So I will fix that real quick. Sorry for any confusion that caused. This will be listed correctly on your thing. But yeah, these were indeed for methane. Boop. I forgot that I had changed this, but not changed the titles for these. Okay. So, there. These are for methane. So, and I think I got all of them. So that means that we have, it's around 16.05, or 16.06 grams per mole. So, that means, let's do a quick calculation. So if we have, I'll write it over here. Come on, pen. No, come back, pen. Okay, so if we have 10 grams, and we've got CH4, we're going to have 16.05, sorry, not 06, grams per 1 mole. When we do that, we take 10 and we divide it by 16.05. I'm going to get that we have 0.623 moles of methane. So now we plug it into here. We have 0.623 moles. And we're going to multiply that by negative 1.37 kilojoules per mole. And when I do that, so it's 0.623, don't miss the decimal, times negative 1.37. And from there, I'm going to get that this is negative 0.854 kilojoules. That's our answer for number 2. Then we have our third step, which is now we are going from 33.34 to negative 55. And so for step 3, we're again going to use Q equals MC delta T. Remember that you've turned all of it into liquid, so all the mass is still there, so you still have 10.0 grams, but your specific heat is going to change. This is because you're now in the liquid form, so you need the liquid specific heat, which is 4.75 joules per gram Kelvin. We're then going to have a delta T we've got to figure out, which is going to be, when you convert it to Kelvin, 218 Kelvin minus 239.66 Kelvin. We can then plug all of this into our calculator, and we are going to get negative 1,029 joules. And I'm just going to go ahead and round this to negative 1.03 kilojoules. Now we just need to add these three together. So our total heat is going to be equal to negative 1.20 kilojoules minus 0.854 kilojoules minus 1.03 kilojoules. You'll notice they're all negative since all are about removing heat, none are about gaining heat. So make sure you get your signs right when you're putting them in your calculator, or you might end up with a very different number, especially if you leave the 1.2 as positive, you'll end up with a number that's fairly off. So when I do that, I get that my total energy is going to be negative 3.08 kilojoules. So this is going to be the amount of heat lost if I want to take 10 grams of gaseous methane and change it from 25 degrees Celsius to negative 55 degrees Celsius. Note that this does take a little while, so you want to get used to be able to organize these problems. You'll notice it was very systematic in nature. These are done very similarly. You're always looking for, when do you change the temperature, when do you change the phase? And once you've done one, you're always going to do the other next. Like if you did a cooling or heating step, next is going to be a phase change. You're not going to have 2 phase changes in a row when we're looking at this. So once you find your first step, that'll direct you what you should do until you get to your last step. And just don't forget to add everything up together at the end. So we've got one more problem to look at. So let's look at a phase diagram design problem. You did something like this in workshop, I believe. So I want to draw a phase diagram for an unknown material where these 5 points of information are true. Note, I'm not going to be strict on your drawing because, gosh, I'm not great at it either, I know. It's really hard if you're not using a computer and doing it by hand. But we want to identify these points so that we know that we're doing something with it. So I'm going to start by identifying my triple point. So I suggest identifying all the points before drawing any lines. So I'm going to say, right here is going to be 0.650 atmospheres. Don't worry about your scale too much. Just make sure things are in the right order, if that makes sense. Like, these aren't going to be perfect scales, but it's important that 12 not come after 13. That's all. So here is going to be our triple point. We know everything has to come through that. We then know the normal melting point. So remember, all the normal ones are going to go at 1 atmosphere. It's going to happen at 13 degrees Celsius. So for that, I'm going to try to draw a dot that's just a little right of 12. And then I'm going to draw a line. And I'm okay if you do it a little further, 13 degrees Celsius. In retrospect, I should have had 2 little lines like arrows pointing to them to make them easier. Because your melting point tends to be pretty close to your triple point. It's a fairly sharp curve a lot of the time, a fairly sharp slope a lot of the times. So now let's identify the normal boiling point, which still occurs at 1 atmosphere, but it's going to happen over here. That's going to be my 94 degrees Celsius. Then we have a few more points we've got to do 2 atmospheres, and we have to do a point at 1.6 atmospheres. So at 2 atmospheres, at, let's see, 15, it's still supposed to be freezing. So that needs to be the point where that's along our solid curve. So we've got that. So again, we've got a mark like right here, and I'll put an arrow to that, 15 degrees Celsius. And then we have to finally mark our critical point, which occurs at 1.6 atmospheres and 189 degrees Celsius. So I'm going to put that out here. So there, let's see, 189 degrees Celsius. Do your best to identify all these points. And so one thing you can even help is for like my 1 atmosphere point, I'm going to draw some dotted lines to help identify where I wanted them to be. Same here. And then finally, we've got this one. And then finally, this one. I know there's a lot of lines here, but this can help identify that, yes, I do indeed mean those points. So now let's draw things. My triple point, I have to come from here. That is going to be my solid. So this is my first line. Now I need to keep it freezing between solid and liquid, so it's going to go. Okay, that was very poor. I don't know how to erase just part of the line. So, okay, if I had a pencil, I would erase part of that line. But it needs to go straight up to here. And then it should go up to here. I have never tried to draw on a tablet a phase diagram. This is hard. So I will do one in class that is more reasonable. No, don't do that. And then this line is a bit easier because the slope's not so high. We just go there. And remember, this point actually stops when you get to the critical point. So this one is going to keep going forever, but the critical point stops. And so this would be a reasonable phase diagram. No, if you're on your test, you need to use an eraser. Erase, don't have random squiggles here, right? Or if it's with a pen, you can go ahead and redo it. This is just trying to draw on this tablet. It's hard for drawing phase diagrams. So hopefully that helps with chapter 11. I know there were 5 questions, and some of these are kind of long ones. So I wanted to go through each of the sort of long processes to give you a feel for how to do these.